Hello guys, so welcome back to our tutorials. Basically, today we're gonna solve another example in Cedra's book. Basically, it was homework 20. So in this homework, we have again common emitter amplifier. And why it's common emitter? Because again, the input here, the signal, is as an input current toward the base, and the output or load is connected to the collector. Okay. What's not mentioned is the common thing, which is the emitter in this case. Okay. So in that problem here, we have some resistors that are known for us, but in the other way, we know some of the currents. So IE is given 2 milliamperes. I1, which is flowing in R1 here, and I2, which is flowing in R2, are approximately equal to each other, equal to 0.2 milliamperes. When I say they are approximately equal to each other, that means we neglect IB. That doesn't mean IB is equal to 0, no, because basically IE here is given, it's 2 milliamperes. And if you divide 2 milli by 100, which is beta, it will be 0.02 milliamperes. And look here, I1 and I2 is 0.2 milliamperes. So they are 10 times bigger than or greater than IB. And that's an acceptable range to say that some value is much greater than another value so that we can neglect this other value. Okay, so here I1 and I2 is 10 times greater than IB, so we can neglect IB, in reference to I1 and I2. So we can basically consider R1 and R2 are in series. So that's basically the basic conclusion from that R1 and R2 can be considered as series resistors. Okay. Okay. So let's check what's, and also given here, VCC is 15 and the overall voltage gain, it's minus 40. The overall, which is V signal, I'm sorry, V output over V signal, or EV multiplied by R input over R input plus R signal. So let's see what's required in that problem. First, R2 is required. This resistor here, R2, is unknown. So let's try to solve it. Let's try to get it. Okay. So it's given here that VB, the voltage at the base, is equal to 5 volt, or VCC over 3. This is the original question, but VCC is 15, so it's equal to 5. 15 over 3 is 5. So the current I2, which is flowing in R2, equal to this point minus this point over R2. The first point is VB. Second point is the ground, 0 over R2. I2, remember, is known, it's 0.2 milliamperes. And the VB is known. VB is 5. And R2 is unknown. So here is basically the unknown here is, we have only one unknown, which is R2. So we can determine R2 from that equation. It will be basically 5 over 0.2 is 50 over 2, it's 25 kilo ohms. Number 2. Find R1. So I1 is flowing in R1. Okay. So it's flowing in that way. So it's equal to that point, which is VCC, minus this point, which is VB again, over R1. So I1 equal to VCC minus VB over R1. So equal to VCC is 15, VB is 5, it's known, over R1. And remember, I1 is known, is 0.2 milliamperes. So again, we have only one unknown here, which is R1. So this will be 10. We're going to divide 10 by 0.2, multiply 10, numerator and numerator. So it will be 100 over 2, it's 50 kilo ohms. So R1 will be 50 kilo ohms. Simple. Number 3, RE. Find RE. So here is RE, in which IE is flowing. And remember, in DC, that capacitor is open circuit. So you can just remove it completely from the circuit. IE is flowing in that way, so it's equal to that point minus this point over RE. So IE, which is known 2 milliamperes, equal to this point, the first point is VE, which is unknown for us, minus 0 over RE. Or VE over RE. And for the first time, we have two unknowns. So when we calculate R1 and R2, we have just one unknown. It was easy or simple. This one is not. We don't know VE. But if we look here carefully to the circuit, we know VB. And we know that this voltage here is VBE 0.7. So VBE is known 0.7 equal to VBE minus VE. The voltage difference between 2 points is basically the first point voltage minus the second point voltage. VB is known. It's 5 volt. VE is not. So 0.7 equal to 5 minus VE, just one unknown. So VE from that is 4.3 volt. So that's basically, it's 4.3 over RE. Now we have one unknown, which is RE. So RE will be 4.3 divided by 2, which is 2.15. So from that, RE is 2.15 kilo ohms. Simple, again. You don't need even a calculator. Number 4 and 5 is really simple, GM. Since you have IE, so approximately equal to IC because beta is 100 big. So this is equal to GM is equal to IC over VT, right? Wrong, yes, IC over VT. IC approximately equal to IE over VT. Remember, IE is 2 milliamperes. We usually define VT as 25 millivolt, sometimes 26, will not have a big difference. Okay, so this will be 80 milli ohm minus 1. Number 5 is also simple, R by. We're going to use either GM or R by in our EC analysis. So R by is, that's a resistance. So VT, the voltage should be divided by current. And the current is IB. VT is known, 25 millivolt. I'm sorry, this is 25 millivolt. Again, I did this mistake last time, so again. Millivolt here and also volt. Divided by IB, which is IE over beta. IE is 2 milliamperes, I'm sorry. And the beta will be in the numerator because the denominator of the denominator is basically a numerator. So it will be 100. And so we have here 2500 divided by 2, which is 1.25 kilo ohms. Or 1250 ohms. That's basically the DC part of this question. Now the AC part. So all the previous here was DC. Let's mark them by putting just DC here. So all of that was just DC. Okay, the rest is just AC. So in the beginning, our input is required. So we need to draw the equivalent circuit. If we, in the AC analysis, we short all the capacitors and we cancel any DC source. We have just one DC source here, which is the voltage VCC. When we short it, it will be just a ground. So this point that was 15 will be just a ground. So that will be the circuit after of course the capacitor will be short, so I'm gonna short it directly here. This is our signal. This is V signal. This is R2, R1, RC. RC is unknown, by the way. And RE. When there was a capacitor across RE, we're gonna short it like this. This is a ground from the beginning. And here is VCC will be also ground. Then we have another shorted capacitor, then RL. So to be complete, this is not complete yet. This is just zero now, because if somebody considers this as an equivalent circuit, that's not acceptable. So we should remove the capacitor and put its equivalent circuit and reconnect the whole of the circuit again. So this is beta IB. This is R by IB, emitter, base, and collector. Now, between the base here and the ground, we have three branches. A branch, a second branch, a third branch. Okay. So we have R1 parallel R2. And we have our signal and the V signal. That's one, part. The emitter now connect. So here is the emitter. As you see, the emitter is just connected to ground, and our RE will just go away. That's it. RC, the collector now is connected, has two branches, RC and RL. So we're gonna draw them. RL here, RC here. And remember, this is VO. And here is VN. And here is our input. Remember, the definition of our input is the resistor that the input source, which is V signal and R signal at the same time. Here is the input source. These two together. And here is the terminals of the input source. So our input and the V input are between the terminals of the input source. So they are different from V signal. Okay. So in number 6, our input was required. And then we know that this circuit is isolated from that circuit. So when we look in that direction here, we just saw this resistor and this resistor, which is, so our input is R by, which is known, 1.25 kilo ohms, parallel with R1, parallel with R2. That's our input. And if we do this, this will be 1.16 kilo ohms. Number 7. In number 7, EV is required. If you do it, you will find that EV as an as a formula is minus beta RC parallel RL over R bar. But this is not acceptable because RC is unknown. So we can't use it. So let's go back to the givens here. You will find that one of the givens is GV, the overall voltage gain. And do you know that GV is equal to EV, R input plus R signal. Okay, so this is equal to minus 40 equal to EV, which is unknown. Our input is known, 1.16. Our input is known, 1.16. Our signal is known, 2 kilo ohms. One equation is one unknown, which is EV. So from that, EV is minus 108.96. Very nice. Number 8. Or this was actually, yeah. So in number 8, RC is required. Now we can go back to this equation because EV now is known. Okay, so EV, EV, which is minus 108.96 equal to minus, and the minus should go with the minus. You cannot have a resistor with negative value. Beta, which is 100. Then you have RC, which is unknown, parallel with RL, which is 2 kilo ohms, over R pi, which is 1.2, right? 1.25, yeah, 1.25 kilo ohms. Okay. So here we have just one equation with one unknown. Of course, you cannot, get RC in one side and the rest in the other side in that way. So you should write it in that way: minus 100 over 12.5, and then this will be RC multiplied by 2 over 2 plus RC. Okay, that way you can get RC in one side, of course, and the rest on the other side. So from that, RC will be equal to 4.27 or 4.2 kilo ohms. Finally, number 9, AV note. AV note is really simple, because it's a limit. RL goes to infinity for AV. Okay, so if RL goes to infinity here, EV note will be minus beta RC over R bar. Minus beta, which is known, 100, RC, which is known now, 4.2, over R pi, which is also known, it's 1.25 kilo ohms. Here it is. No. Okay, so let's do it: minus 100 multiplied by 4.2 divided by 1.5. This will be minus 338.4, and it's a dimensionless. Don't write volt there. You can write volt over volt to give a hint that this is a ratio. Okay, but it's a dimensionless basically. Okay, guys, that was basically homework 20. It's simple, just as the previous ones. Maybe the next one, homework 21, which we solve tomorrow, it will be a little bit harder, not harder, a little bit harder. Okay, guys, thank you very much, and see you soon. Bye-bye.